Thank you. Good afternoon. And also a deep thanks to the organizer for inviting me here, for giving this talk. Today's talk will be about the problem of reduction of multisymplectic manifolds with respect to symmetries. And this is based on a joint work with Casey Black and Leody Rybkin, that is here, that has appeared on arXiv 2 months ago. So it's quite new. And let me start quite slowly by dissecting the title, right? So symmetries and reduction of multisymplectic manifold. So what is symplectic? Symplectic is a symplectic structure, is a geometric structure providing a prescription of how to measure the area of two-dimensional surface element embedded in a manifold. So it's a fairly well-known framework, but here we are talking about multisymplectic. It is one among many possible generalization of this notion, and in particular, it extends symplectic by considering differential form. I mean, the prescribed differential form is degree greater than 2, while in the case of symplectic, you consider closed non-degenerate 2 form. And by symmetries, we mean a group of transformation preserving the prescribed geometric structure. So in this case, the multisymplectic structure. And what we mean by reduction is a procedure providing another manifold of reduced dimension, encoding the relevant geometric structure out of the given symmetries and starting, I mean, the multisymplectic structure that you are starting on. So as I said, multisymplectic is a generalization. I mean, it's a possible generalization of symplectic. So let me briefly recall what we want to generalize. So let me, start by recalling something about symplectic geometry. So what I really like is to take a mechanics flavor approach. So the key definition in symplectic geometry is the definition of symplectic manifold. It is a pair of a smooth manifold together with a non-degenerate closed 2 forms. And why this is connected to the mechanics, you can see this in the key example, the example of the cotangent bundle. Take any smooth manifold Q, the cotangent bundle of Q is naturally symplectic via taking the external derivative of the so-called tautological 1 form. And so why this is connected to mechanics? Let's consider my favorite system, the pendulum. The configuration space of the pendulum is the set of all possible displacement of the system. And this can be encoded by a manifold. Let's say that this is Q. When you construct the cotangent bundle of Q, you get something of 1 dimension more in this case, because the system has 1 degree of freedom. Out of that, you get something that is 2-dimensional. And this 2-dimensional space is called the phase space because it's encoding the physical state of the system, while configuration is something different from states. So in other terms, symplectic geometry is connected to the geometric approach to mechanics based on the notion that states are point of a symplectic manifold. So there is a geometrical side of this picture, but there is also an algebraic side. So an algebraic approach to mechanics. So you introduce the other object that is called classical observables, and mathematically is the unital associative commutative algebra of smooth function over M, over the symplectic manifold. And out of this data, I mean, having fixed a symplectic form, you can introduce a special class of vector fields that are called Hamiltonian vector fields that has the property that when you introduce this vector field into the prescribed symplectic form omega, you get something that is that. And so there is you can associate to any smooth function Hamiltonian vector fields, and that's it. I mean, this is the logic. So out of the prescripted form, you can define a special class of Hamiltonian vector field pertaining to any smooth function. And remember that smooth function can be interpreted as classical observables or measurable quantities. So out of this data, you can construct the Poisson algebra of observables. So you add over this associative algebra another Ali bracket that is called the Poisson bracket. This simply constructed out plugging in Hamiltonian vector fields into the symplectic form. So the upshot, there are two. There's a duality between a geometric approach to mechanics basic on states and an algebraic approach to mechanics basic on notion of measurable quantities. And mathematically, we talk about Poisson algebra observables and the smooth manifold. Okay, these are the framework we want to generalize to the multisymplectic setting. So what does it mean to pass from symplectic to multisymplectic? So the slogan is that multisymplectic means going higher in the degree of omega. So the key definition is this one. So an symplectic manifold is a pair M given by a smooth manifold together with a non-degenerate closed n+1 form. So n-plectic, you fix an n+1 form. And this family encompasses a huge class of examples. So it's range from symplectic forms, where you take n equal to 1, so one plectic mean symplectic, up to the higher possible form, volume forms, where n is the dimension of the manifold -1. And I mean, the class of examples ranges between these two extrema, so there are a lot of examples here. But, so this conference is about higher structure and field theory, and that's what, so multisymplectic is quite fit in this context because the historical motivation for introducing this object comes from the mechanics, so the geometrical formulation of first order field theory. So we can try to draw a dictionary where in mechanics we have this notion, phase space, observables, and symmetries. When you consider point-like particle systems, so system with a discrete set of degree of freedom, you can make it correspond to this notion coming from physics, this well-defined notion in mathematics. So this phase space is a symmetric manifold, observables in a Poisson algebra, and symmetries group section admitting a comment map. So what's the point? If you consider then field theoretical systems, so system with a continuous, infinite and continuous degree of freedoms, you can say, you can associate to the phase space a multisymplectic manifold, to the observable, another algebraic structure is called an infinity algebra of observables. And again, you can talk about group action admitting some version of the comment map. So, yep. Sorry for. Okay, I will tell you later. There is a slide on this, just to set. I'm just setting the framework, so it will come. Okay, so what's the idea? What's the plan for this talk? There will be three subsections. The first one will be about a quick review of the basic notion of multisymplectic geometry. The second one will be another review part where we'll discuss the regular reduction scheme in multisymplectic geometry. And in the last step, I will try to discuss the contents of our paper, so where we introduce the notion of singular reduction scheme for multisymplectic geometry. Okay, so let's start with the basics. So basic notion of multisymplectic geometry. I already said what is an symplectic manifold, so a pair like this. What does it mean to be non-degenerate here? Means that if you consider the flat bundle map, so the map that you get from the tangent bundle to the wedge of the cotangent bundle by plugging in the vector field inside the form, it has to be injective. So this is the answer. This is the non-degenerate part. So key example, when n is equal to 1, all of this boils down to be a symplectic manifold, really, because n equals to 1 means that I have a 2 form here. When n is the basically the top dimensional allowed for the system. Omega is a volume form. And the other key example coming from mechanics is the following, that if you consider a smooth manifold Q, you can construct the multi-cotangent bundle by wedging n times the cotangent bundle of Q. And this can be proved that this one is naturally emplectic. And there is a famous or infamous construction given by Gimsit. This is an acronym. These are named Gautier, Isen, Marsden, etc. They give a construction, they give a procedure to construct out of any configuration bundle, so out of any classical field theory, a multisymplectic manifold. So there are plenty of examples, there are some more. So, okay, so the idea was to introduce the basic concept. So what can we do when we have a fixed n+1 form? So the first idea is that with a prescribed form, we can recognize special classes of smooth objects. For instance, we can talk about Hamiltonian vector field that are vector field on M, such that when they are introduced, when you plug them in omega, you get an exact form. And multisymplectic is something similar, but you get a closed form. And while in the symplectic case, we only talk about Hamiltonian vector fields, in the emplectic, we can, let me say again, in the symplectic case, any smooth function is Hamiltonian because any smooth function admits an Hamiltonian vector field. In the case of multisymplectic manifold, this is not the case. So we select the special class of Hamiltonian n-1 form, and these forms are such that there exists an Hamiltonian vector field or a vector field, such that the two of them, vector field and form, satisfy this equation. It's the same equation defining Hamiltonian vector field in symplectic setting, but now the forms are in higher degrees. So another fairly easy observation is that if you fixed a multisymplectic form, it's natural to characterize action that preserve the structure. So you can talk about multisymplectic Lie group action. These are smooth actions such that they preserve the differential form. And also you can talk about infinitesimal Lie group action or multisymplectic Lie algebra action. So these are Lie algebra morphism from the Lie algebra of a Lie group to the space of vector fields over M, such that all the fundamental vector fields preserve omega. And as an aside, when going to the multisymplectic framework, you can see that there is an hierarchy of conserved quantities. You can talk about differential forms in any degree and define notion of being conserved along a vector field by the fact that the derivative is exactly 0, or is an exact form, or is it a closed form. So there is a hierarchy of notion of conservation here. Okay, so I need this because I want to now go to the algebraic counterpart of this picture. So define what is the multisymplectic analog of the observable algebra. So the main point, we start from the the key ingredient. These are Hamiltonian forms. These are the differential form that I defined before. So such that there exists a vector field such that the two of them satisfy an equation that is called Hamilton de Donderweil equation. And out of this, you can construct two algebraic structures. The first one is called Observable's Elefinity algebra. And basically, it starts from observing that this space can be endowed with a binary bracket given by insertion of the two Hamiltonian vector fields into omega. And this binary bracket does not satisfy Jacobi, but satisfy Jacobi in a controlled manner. This can be proved that starting from this, you can complete it to a full Elefinity algebra. So what's happening here is that we still have a skew-symmetric bracket. Actually, we have many skew-symmetric brackets, but here we are losing the possibility of you cannot multiply any observables anymore, because while C infinity of M is a natural notion of algebra by the pointwise product, we are missing this structure here. And as I already said, Jacobi is not valid anymore, but is valid up to exact terms, so up to motopies. But you can also construct another structure that is called observable Leibniz algebra. Well, basically, you take the same space and you endow it with a different operation. I mean, you take the Lie derivative of the first Hamiltonian vector field into the second one. So this expression is manifestly is not symmetric. So in this case, we are losing the skew symmetricity. Again, we don't have multiplication, but these brackets satisfy Jacobi. So there are these two possible choices of observable algebra. Okay. So a little bit of details. So what is this L-infinity algebra of observables or multisymplectic manifold? This is a construction given by Rogers, and it consists of a conchain complex L that is given by a shifted truncation of the Theorem complex, shifted because in degree 0 I'm putting n-1 form, and in particular in degree 0 I'm not considering all Hamiltonian form, all differential form, but only the Hamiltonian ones. So this is the underlying chain complex. This is endowed with a collection of n skew-symmetric multibrackets. So for instance, the kth multibracket is the only non-zero component of this multibracket defined on this graded differential space is given by taking k Hamiltonian forms, and then you plug the corresponding Hamiltonian vector fields into omega. So these are the data. I mean, I'm not saying anything, but I just say there is an infinity algebra. So quickly, what is an infinity algebra? The slogan of infinity algebras is the notion that one obtains from a Lie algebra when one requires that the Jacobi identity has to be satisfied only up to an higher coherent chain homotopy. So in more simple terms, we could say an infinity algebra is a pair where L with multibracket, where L is a Z-graded vector space, and this mu K is a collection of homogeneous ski multilinear map. So in particular with this degree shifting, I mean, they are not in degree 0, but the kth one is in degree k minus 2, together with axioms, and this axiom is called the higher Jacobi equation that basically tells you that if you combine, several combination of plugging in E multibracket into the J, this something is equal to 0. So, okay, this expression could be complicated, but just to say that is a higher version of Jacobi. And Rogers proves that the higher several algebra, so the thing that I defined in the previous slide, actually forms an honest and infinity algebra. And that's it. I mean, these are the details I already said, because the underlined graded vector space here is a truncation of the Theorem complex. Okay, so this is the L-infinity part, but there is also the Leibniz part. What is the Leibniz algebra of observables? Again, is a vector space of Hamiltonian forms together with the binary bracket. And these objects satisfy interesting properties. So, for instance, the mapping Hamiltonian forms to Hamiltonian vector field is a Leibniz morphism, so preserve the bracket. The second property is what defines a Leibniz algebra. So the Jacobi identity holds. And the third equation tells something like, express the fact that this binary bracket, so wait, there's a typo here. We don't have many brackets, only one. Only one with 2 entries. So the last equation tells us that if you symmetrize this binary bracket, you don't get 0. So this bracket is not skew-symmetric, but you get something that is an exact term. So there is something up to homotopy also here, but it's not in the Jacobi sense, but in the skew-symmetric sense. Okay, the upshot is that there is a dichotomy of possible notion of observables, and we are still working on understanding what is the good one. I mean, if maybe there is a third structure that encompasses these two. We are still working on this. But let's stick with these two notions. Okay. We need them because now we want to talk about reduction. So before talking about multisymplectic reduction, let me recap what is reduction in the symplectic setting. So let's now, so n be equal to 1, so I'm considering m to be one plectic or another term symplectic. So I call theta a smooth group action on m, and with this underlined, I consider the corresponding infinitesimal action. So it's instrumental when dealing with the reduction to introduce the notion of moment map. So what is an equivalent moment map? Is a smooth map from the smooth manifold M to the dual of the Lie algebra, such that the conclusion says that it is equivariant, so that's why it's equivalent in the name. And the third condition said that if you consider the smooth function that you get out of in pairing this covector with an element of the Lie algebra, you get a smooth function, and this smooth function has a corresponding Hamiltonian vector field, and the Hamiltonian vector field is the fundamental vector field pertaining to the action. So there is this compatibility, but together with this notion, there is also a dual notion called comoment map, that is a linear map from the Lie algebra to the associative algebra of smooth function over M, such that, again, map element in the algebra into smooth function, so into observables, such that the corresponding Hamiltonian vector field is the fundamental vector field. And the third equation tells us that this map is a Lie algebra morphism. So it's a morphism in the category of Lie algebra, because this is clearly a Lie algebra. This is a Poisson algebra, so in particular it's a Lie algebra. Okay, so the upshot of this is that how can you see this more conceptually is that you can see that the comoment map mu tilde can be seen as a lift of the infinitesimal action, so this map, along the assignment of Hamiltonian vector fields, so the map that map function into Hamiltonian vector fields inside the category of Lie algebra. So why I'm giving this diagram? Because this diagram is easy to generalize to the other setting, so the multisymplectic setting. And in a word, why is this two are dual? Well, they are dual with respect to the so-called carrying operation, because this is an operation from mapping, say, a set into a set of function. This is the same. So the uncarrying is transforming this map into a function with two entry into a single one. But I mean, this is immaterial now, only to say that in some sense these two are dual. Okay, as I said, these tools are instrumental for reduction. So what is symplectic reduction? It's a procedure associating to any suitable regular pair of symplectic manifold and Hamiltonian action, another symplectic manifold of smaller dimension. And there is a key result, I mean, pivotal theorem that is called Marsden-Weinstein reduction. It tells us that even as a datum, a symplectic manifold and a symplectic action admitting an equivalent moment map, if you fix an element in the dual of the Lie algebra, and this element is a regular value, so in particular this means that the pre-image along the moment map is a smooth embedded manifold. And if you also assume that the action of the isotropy group of this element on this pre-image is free and proper, so this means that the quotient is a non-honest smooth manifold, you can put on this quotient a symplectic structure, and this symplectic structure is unique in the sense that satisfies a certain compatibility condition with the starting symplectic structure. So these are a recipe to construct another manifold, another symplectic manifold out of the data. And why is it important? Well, okay, this is only a perspective. In mechanics, Why is it important? Because it embodies the process of restricting the dynamics of the system, of a mechanical system, to the level set of the conserved quantities of the system. So, for instance, a very simple example that is very common in physics, and when you restrict the study of point-like particle in a central potential by studying only its radial coordinates. So we are forgetting coordinates, and then in this process can be more rigorous in general, talking about moment map. Okay, this was the sympathetic case. So how can we generalize the previous construction to the multisymplectic setting? Okay, we can do it like this. So consider now a multisymplectic structure on M, on an n-plectic structure. Consider as a group action that preserves the multisymplectic form and denote by the underline infinitesimal action. You can slightly modify the definition of moment map to give a higher notion of moment map. So now we talk about a smooth map from M to G star, tensor n-1, tensor the n-1 wedge of the cotangent bundle. This is to take, we need to add this piece in order to save this equation, because if I want this equation to make sense now, I need to have something that is valued in n-1 differential form. So out of this modification, because we want to keep this equation and try to modify the other condition to have something that makes sense. So the equivalent condition now is required to consider also an action of this space. And there is a third compatibility condition that out of this smooth map, this smooth map is not only a smooth map, but it also has to be a section of the correspondent bundle over M. So this is condition 3. And again, you can construct a dual notion. I will call it simply moment map. While in the previous slide, in the sympathetic case, here we had the smooth, the algebra of smooth function. Now we put in the Leibniz algebra of observables, and very simply, we substitute this, and now this condition is the same as the Hamiltonian equation, and the second one now says that this map is not only a linear map, but is a morphism in the category of Leibniz algebra, because I didn't say that. I forgot to say this before, but Lie algebra are subcategories. They form a subcategory of Leibniz algebra and also of Elefinity algebra. So it makes sense to look at this map. Look at this object as an object in the category of Leibniz algebra. So again, you can read this construction as a lift, but now in the Leibniz algebra category. And again, this is dual in the same sense of before. So with this slight modification of the definition, it's been proved that you can produce a multisymplectic analog of the Marsden-Weinstein reduction. Sorry, yeah, so it depends by the group has to be connected. You can go in that direction. Yeah, I think the answer is positive. It's not something that comes from my work. It's something that has been published by Casey Blacker. But yeah, I think, yeah, it is the same relation as the previous one. This one, okay, theta is the action. So this one is the action on this one by pullback. So taking the pullback of theta g of the differential form. But by the way, this only is to say, I'm saying explicitly that this map is equivariant. Okay, so what I want to say now is that there is an analog of the Marsden-Weinstein reduction theorem. So the setting is the following: let M omega be an empectic manifold. Consider now an action with a moment map mu, moment map like this, a bit like this, sorry. So in the sympathetic case, it was easy to define what is the pre-image of the moment map. You have to be a little bit more careful here. And in particular, we define a regular value of the moment map mu here as a set of points such that the image of the moment map coincide with the image of phi, where phi is an element in the n-1 form valued in G star. I mean, what I want to say is that you can see mu like something like this. So what is a value of this, like a momenta, is again is an element in the same space, and we only require the two agree. Right? So this is the notion of regular value for the moment map. And the theorem, okay, admitting this definition, the theorem of the multisymplectic regular reduction that has been given by Casey Brecker in a paper appeared 1 year ago, as similar structure of the theorem takes a similar structure with several modifications. So the data now is that omega is symplectic, the action is multisymplectic, and is given an equivalent moment map, so something defined in the previous slide. So we define a regular value here as an element of this space. By regulars, we means that this space is mutually embedding, is mutually embedded. The other hypothesis here is that the isotropy group of G with respect to this element act free and properly on this smoothly embedded manifold. And the upshot is that you can take the quotient, so define this quotient, you get a smooth manifold, and there is a natural pre-emplectic manifold. So here, in the higher case, we are losing the non-degeneracy here. So now we get something that is degenerate, but still it satisfies the same compatibility condition. Okay, so, yep. You mean the homotopy momentum map? No, do you mean the dual, right? Well, I cannot. Well, because there's something that I cannot do it, but I see that this is a problem, right? Because we have this choice. Actually, I don't know how to do it, but this is somewhat an upper problem because if you remember, I also gave you the definition of Elefinity algebra of observables, right? So you can construct also a lift in the category of Elefinity algebra, and you get another version of the moment map. It is called homotopy momentum map. So another natural question will be, what is the pre-image of the homotopy momentum map? How can I define regular value of this? And we don't have an answer yet, but I think that one of the talk that has been given here by Christian Broman, probably in the first week of this event, talk about how to define this regular value in the case of multisymplectic manifold that comes from field theory. So we're still working toward a general point of view of this. Okay, so it's time to move to the... Okay, this was the regular setting. What about the so-called singular reduction? So what do I mean by singular reduction? So let's stick for a bit to the sympathetic framework. So consider an action that admits a moment map. When mu is singular, that means that you consider a value of in the dual of the algebra, so for instance 0, such that the pre-image is not a manifold. So in that case, the geometrically reduced space may not exist, because I want to recall that the Marsden-Weinstein reduction gives you a symplectic manifold. So when the reduced symplectic manifold does not exist, it makes sense to ask ourselves if one can construct a reduced algebra of observables out of the given data. But we don't want to construct any general this object. We want this object to be compatible with the regular case. So in particular, it's important to ask that the corresponding reduced algebra of observables has to correspond to the algebra of observables of reduced manifold when 0 in this case is a regular value. So as to agree with the regular construction. So an example of singular reduction in the symplectic case is given by the so-called Tiske-Weinstein reduction. So is a construction that runs like this. So the data are given a symplectic manifold and an action on M with an equivalent moment met mu. Out of this data, you can construct another algebra that admits a Poisson algebra structure such that it agrees with the Poisson algebra corresponding to the Marsden-Weinstein reduction when this kind of reduction exists. So in particular, this is constructed by, there are several schemes of singular reduction. I'm only giving here an example. And this example runs by construct first an associative algebra by the quotient of the algebra of observables with this ideal. This is the ideal, the associative ideal generated by all the momenta, so all the possible image of the momentum map from the domains of the Lie algebra, right? So you can construct this Lie algebra, this associative algebra. Then you consider the G invariant elements, and it can be proved that taking this G invariant element, you get again a Poisson algebra. So this is an idea. Just to say that there exists singular reduction scheme, but we cannot generalize these constructions directly to the multisymplectic case, because in the multisymplectic case, one should put here the Leibniz algebra of the L-infinity algebra of observables. But in that case, you are missing the associative structure. So you cannot construct this object, and in particular, you cannot construct this quotient. So we need a different strategy to realize the singular reduction in the multisymplectic case. Okay, so what's the idea? So how we managed to construct a singular reduction? This is the roadmap. So our data was fixed. Okay, it's not written here, but consider M to be a multisymplectic manifold. Then consider a constraint set N that is simple, a closed subset of M. So it's not a submanifold in general. And also consider an infinitesimal group action preserving N. So out of this data, our goal was to obtain a reduced observable algebra out of this. And how can we do that? The strategy is the following. First step is to try to understand what does it mean to be tangent to a closed subset. So when N is a submanifold is clear, but when N is general, for instance, when N is a singularity or N is something like a cross in R2, how can you define what is smooth? So it's possible to give an algebraic-based definition of this. So after that, you can talk about smooth field and form that vanish along N. And out of this idea, it's possible to define a class of reducible fields by requiring to preserve the vanishing object, and also define a class of reducible forms by requiring that they are conserved with respect to the infinitesimal action. So combining these two, you can get a receipt for recognize the reducible observables and vanishing observables, and after that, quotienting these two, you get the sought L-infinity algebra. So, okay, so I have time to describe the construction in some details. So the first step was to identify a smooth object on a singular set. So consider N to be any closest subset of M. Now introduce the ideal of smooth function vanishing over M. We use this device with item as a device to identify vector fields tangent to N. So in particular, a vector field tangent to N is a smooth vector field over M such that it preserves the ideal of function vanishing over N. So these are an example of a closed submanifold. A closed subset N inside of a manifold that is R2. So in blue, I basically represented what does it mean to be tangent to M. Here is visually clear. It's something that is smooth in general, but when you restrict it to N, you get something that is also smooth on this, for instance, on this branch. The problem comes from these singularities. So that's why we took this algebraic approach, because we are putting under the rug the problem of singularities. So in the same algebraic way, you can also define what does it mean to be vanishing, a vector field to be vanishing over N. It must map, I mean, the lead derivative of any smooth function along this field has to be something that vanishes over M. And when N is smoothly embedded, you can interpret the vector space of vector fields, of smooth vector fields over N as a quotient of the vector field tangent to N modulo the vector field vanishing on N. And out of this data, you can also introduce the notion of differential form vanishing on N. These are smooth differential forms over M, such that when you plug in vector fields that are tangent to N, you get something that vanishes over N. So this is an algebraic framework to make sense of being tangent to something that is not a manifold but is only closed. And okay, out of this data, you can start to talk about reducible objects, right? So the framework is the following. Consider now an infinitesimal action of the Lie algebra over M. I denote with G underline the fundamental distribution. Sorry, this action is by vector field that are tangent to N. So the fundamental distribution in particular lie inside the vector space of vector field that are tangent to N. And I also call with this matfrac G the C-infinity model generated by the fundamental distribution. So this item is instrumentally defined. What does it mean for a vector field to be reducible? So a reducible vector field is a vector field along N. So this is the first equation, such that it preserves the fundamental module. So along N, that's why I'm adding this piece. This piece is that this is preserved modulo elements that vanish, modulo vector field that vanish over N. And similar faction, we also define reducible form. And these are such that to be preserved, I mean locally preserved, so locally preserved along the action. So locally, because this is not zero, but it's something that vanishes over N, and also horizontal in this sense. Okay, and putting this notion together, we can talk about reducible Hamiltonian forms, because these are Hamiltonian n-1 form, such that the form is reducible, and the corresponding Hamiltonian vector field is reducible in this sense. And in particular, it's never true that the first condition implies the second or the opposite. So these two are independent. So these are the recipes for constructing reducible observables. And what's the upshot? Out of this data, we can construct Elefinity algebra of reducible observables, simply by putting in degree 0 the reducible Hamiltonian form and in the other degrees reducible form, because if you remember, the Elefinity algebra of observables was a truncation of the Theorem complex, and here we are considering this truncation, I mean, a subcomplex of this truncation consisting of differential forms that are reducible in our sense. And similarly, you can construct an Elefinity ideal of vanishing observables. And the key result is that, I mean, the key result was, I mean, we gave a recipe to construct these two. The result was to prove that this was an ideal in some sense. I mean, an Elefinity ideal in the simplest sense. This is an Elefinity subalgebra. And out of these two data is automatic to say that you can take the quotient is an Elefinity algebra. So, and this is our notion of singular reduction of observables. So, well, I'm quite ahead of time, but anyway, concluding remarks, I've given you a singular reduction. And this singular reduction indicates that the constraint set comes from the preimage of a co-moment map. And if the value is regular, I took 0 here, but it could be other, let's say 0. If 0 is a regular value, can be proved that the multisymplectic regular reduction agrees with the multisymplectic singular reduction. And, well, I gave you a receipt for n-patic manifold. It's natural to ask what does it mean in the one-patic case, so in the sympathetic case. And it can be proved that the multisymplectic singular reduction in the one-patic case does not give you this Tiske-Weinstein singular reduction, that it was the reduction I gave you before. But this is not bad, but there exists a canonical post-algebra morphism between these two. So in other terms, what I gave you in the multisymplectic setting gives you something that is also new in the symplectic setting. And I think that's all for today. Thank you for your attention.